In the previous video, we talked about inelastic collisions, and we solved the problem for completely inelastic collisions. Today, we're going to deal with elastic collisions. So an elastic collision is when things interact with each other and uh, kinetic energy is conserved. Now, in real life, other than in quantum mechanical things, kinetic energy isn't truly conserved. There's always some energy that goes away. For example, I have had mentioned the example of the in billiard balls. The two balls hit together, and you hear them click. Where did that sound come from? Some of the energy left the system. But in many cases, things lose so little kinetic energy that they're a good approximation to an elastic collision. And so the equations and the methods we're using today will be applicable to those kind of systems that we can approximate as an elastic collision. As we discussed last time, in your standard collision kind of physics problem, you have several parameters. You need to know the mass of each particle, there's the initial velocity of each particle, and there's the final velocity of each particle. And then we have equations that connect them together so that if we know some of them but not all of them, hopefully we can find the others. For two particles, we will have two different masses, two initial velocities, which are potentially vectors, and two final velocities, which could also be vectors. So, for example, if I knew the two masses of the objects and I knew their initial velocities and I wanted to find their final velocities, there are two final velocities, and so there are two unknowns, so I'm going to need two equations. And where do we get our equations from? Well, the first equation is conservation of momentum, because momentum is always conserved in a collision. When we did the completely inelastic collision, we took conservation of momentum, and then we had another equation that was just the velocity, the two final velocities were the same, and that gave us our second equation. Well, that's not true with elastic collisions, but with elastic collisions, we know that kinetic energy is conserved, and so we'll use energy conservation to produce our second equation. So, for example, we can work a problem like this. A baseball with a mass of 145 grams traveling at 20.1 meters per second strikes a tennis ball with a mass of 58.2 grams at rest. If the two undergo an elastic collision, and if the collision is head-on, such that the final velocity of the tennis ball is in the same direction as the initial velocity of the baseball, how fast will the tennis ball be moving after the collision? So in this problem, the head-on collision means it's going to be a one-dimensional problem. We don't have to worry about vectors, which is nice. Also, the initial velocity of the tennis ball is 0. That's going to be helpful. So let's use our conservation of momentum equation and our kinetic energy equation to solve this. So our momentum equation says the initial momentum is equal to the final momentum. The initial momentum is just the mass of the baseball times the initial velocity of the baseball. There's no term for the tennis ball because its velocity is 0 initially. The final momentum is the mass of the baseball times the final velocity of the baseball plus the mass of the tennis ball times the final velocity of the tennis ball. Our other equation is our conservation of kinetic energy equation. The initial kinetic energy is 1/2 mass baseball v baseball initial squared. And again, there's no term for the tennis ball because its initial velocity is 0. The final kinetic energy is 1/2 mass baseball v baseball final squared plus 1/2 mass tennis ball v tennis ball final squared. So now I have two equations and two unknowns. I just need to solve them. To do that, I'm going to first take this momentum equation here, and I'm going to solve it for the final velocity of the baseball. All right, so I'll bring the baseball to this side, and so I'll subtract mass of the tennis ball v tennis ball final from both sides, and then I find that the mass of the baseball times the velocity of the baseball final is equal to this. And then I'll just divide by the final mass by the mass of the baseball to get the final velocity of the baseball in terms of other things. Why did I solve for the baseball velocity instead of the final tennis ball velocity? Well, what I want at the end is the tennis ball velocity. And so if I solve for baseball velocity here and plug it in, that will into the kinetic energy equation, that will eliminate the final velocity of the baseball in that equation, but leave the final velocity of the tennis ball. So I solve for the baseball velocity here so that I can get rid of it and keep the one that I wanted. So now what I'm going to do is I'm going to take my kinetic energy equation and I'm going to stuff this in for the final velocity of the baseball. And there it is. Okay, now next thing I'm going to do is I'm going to multiply both sides by 2. Just there's no point in having all those 1/2. There's one for every term, so let's get rid of them. And then I'm going to multiply out this squared thing here. And when I do that, I notice I get 2 terms here that cancel each other out. Okay? Then I can factor things, like I'm going to take all of the terms that have a v final squared and stick them together. And then here's the term with just v tennis ball final not squared. And notice since they both have v tennis ball final in them, I can factor out a final velocity of the tennis ball and write the equation like this. So I just pulled out this, and here is like I pulled that one of the velocity t finals out from both terms, and then I have this equation here that has to equal 0. Now, when you look at this, there's 2 ways that you can make this equation true, that you can make the left-hand side equal to 0. Either the final velocity of the tennis ball is 0, or this expression here that we multiply it by is 0. And that it makes sense that the final velocity of the tennis ball equals 0 satisfies this equation, because both the initial and final velocities satisfy the momentum and energy equations, right? So if I say the final velocity is equal to the initial for both of them, that's going to satisfy our momentum and energy equations, right? If the velocities are the same before and after the collision, then the momentum will be the same and the kinetic energy will be the same. But that's not the solution we want. That's if the balls miss and they don't actually hit. So the one we want is the other one, okay? And so I'm going to take this, and this is just an equation now I can solve for the velocity of the final velocity of the tennis ball. I can cancel out the mass of the tennis ball, and then I pull this to the other side and divide. And there's my answer. There's the final velocity of the tennis ball. So I just took my conservation of momentum, conservation of kinetic energy equations, and did 2 equations, 2 unknowns. Okay, for a general two-body elastic collision, we're going to try and find just the general solution to this for any 2 bodies that undergo an elastic collision, right? This could be, our tennis ball and our baseball, but now the tennis ball is moving or whatever. This could be an asteroid that comes and interacts with the sun and goes around the sun and goes out in some other direction. Any sort of elastic collision with 2 bodies, we want to come up with a general formula. How could we do that? Well, we have our 2 equations. We have conservation of momentum and conservation of kinetic energy. So the momentum equation, it's just going to be the initial momentum is mass 1, initial velocity 1, plus mass 2, initial velocity 2, and that's equal to the final momentum. All right, but now my velocities are vectors. Then I have the kinetic energy equation, right? So the initial kinetic energy of ball 1 plus the initial kinetic energy of object 2 is equal to the final kinetic energy of object 1 plus the final kinetic energy of object 2. So now I just have to solve this, right? I have 2 equations, and let's assume our 2 unknowns are the 2 final velocities. Let's assume I know the masses and the initial velocities. Can I solve this? 2 equations, 2 unknowns. In principle, yes. But if you look at it, it's kind of tricky because these are vectors, right? This is really 3 equations. There's one for the x component, one for the y component, one for the z component. So it's going to get messy. Plus I have, when I write these out, I'm going to have my different components. And in my kinetic energy equation, I just have magnitudes. In the kinetic energy equation, the velocities are squared. In the momentum equation, they are not. And this can be tricky. So how are we going to solve this? First of all, for this class, we're going to stick with one-dimensional elastic collisions. We're going to then not have to worry about vectors in the momentum equation. And then with that simplification, there's several methods we can use to try and find the final velocities in terms of the masses and the initial velocities. One way to do that is to work in a reference frame where one of the initial velocities is 0. So as we talked previously, when we talked about the center of mass frame, we mentioned that the laws of physics are the same in any inertial reference frame. In other words, if I'm working this problem and I've got these objects moving, I can do all of the calculations in another reference frame, so maybe I'm, sitting in my living room and doing calculations, doing an experiment, as somebody goes running by at a constant velocity. In their reference frame, all of the velocities are going to be different than what they are in my reference frame. The laws of physics still apply. And so we could transform into a reference frame. We could run alongside the collision such that one of the initial velocities is zero, and in that reference frame, the calculations will be easier. In fact, we've already solved the problem where one of the velocities is zero. But in this case, we solve the problem and then we have to transform back to see what happens in the original reference frame. We could also transform into the center of mass frame, solve it, and then transform back. It turns out that that's a good way to do it as well. There's also, without transforming into any different reference frames, we can solve it in the original reference frame using a cool factoring trick. All right. And then a fourth way that I'm going to tell you about how to solve these problems is just remember one of the solutions you got, one of these other methods, and always remember that. Write it down on your note sheet. And then whenever you have a two-body elastic collision problem where you know the initial velocities, you need to find the final, you've got your solution. That is less useful if you know one of the initial, one of the final, and you're trying to find the other initial and final, or if you're trying to find the masses or something, right? So you need to understand these other methods so you know how to manipulate things, but it's also nice to already have the solution. Okay, so the first way we're going to, from this point on, we're just going to be an example problem at the end, but we're going to spend a bunch of time just going through the math and algebra of how we solve these things. It's kind of dry, but hopefully the principles are obvious and you see how we're doing this so that you can understand how to work these types of problems. So first we're going to show the problem where I know the initial velocities and I want to find the final velocities, and we're going to do this by working in a reference frame where one initial velocity is zero. So the way that this works is first we convert our velocities into what they would be in this other frame, the frame in which the initial velocity of particle 1, say, is zero. Then we solve that problem in that frame, and then we convert back to the original frame. So let's do the first thing. We're going to convert the velocities into this reference frame that is moving with the initial velocity of particle 1. Now, to keep track of which velocities are in which frames, I'm going to use W to represent the velocities in the transformed frame. All right, so if I'm transforming into a frame that's moving at some velocity v1 initial, all my velocities are going to change by that amount. So to get my velocities in my new frame, I just subtract v1 initial from everything. So in the W frame, in the v1 initial equals 0 frame, v1 initial gets transformed to v1 initial minus v1 initial, which is 0. So w1 initial, the velocity of particle 1 in that frame, is 0, and that's what we wanted. The initial velocity of particle 2 in that reference frame is the initial velocity of particle 2 in the original reference frame minus the initial velocity of particle 1 in the frame, right? And so all of these velocities in the other reference frame, I just subtract off the velocity of my frame, which is going to be the initial velocity of particle 1. So now I know how to transform those velocities. I'm not actually going to plug in numbers and do this. I'm just establishing the transformation. This is how I do it, all right? So now I'm just going to, in this frame, I'm going to solve the problem in that frame. And this is just like what we did before with the tennis ball and the baseball, because in this frame, object 1 has no initial velocity. So the momentum equation is just mass 2, initial velocity 2 equals mass 1, final velocity 1 plus mass 2, final velocity of 2. All right, and there's our momentum equation. The kinetic energy equation is similar. Once again, we went into a reference frame in which the initial velocity of the first object was 0, so there's no kinetic energy term for the first object on the initial side. All right, but then we have the initial kinetic energy of object 2, and that's equal to the final kinetic energy of object 1 plus the final kinetic energy of object 2. And just like we did before, we're going to take the momentum equation and I'm going to solve it for one of the final velocities. All right, so let's solve for the final velocity of object 2. So I'm going to take mass 1, initial velocity 1 to the other side, and then I can divide both sides by m2, and now I know the final velocity of particle 2 in terms of the initial velocity of particle 1, of particle 2, and the final velocity of particle 1. So I can plug this into my kinetic energy equation over here and completely eliminate the final velocity of particle 2 from that equation. All right, and I do that. I multiply everything by 2. I'm going to expand this squared here. When I do this, I find that there are two terms that are the same on either side of the equation. I can cancel those out. And then I'm left with 0 equals a bunch of stuff times the final velocity of particle 1 squared minus some stuff times the final velocity of particle 1. And so once again, I can factor out a factor of the final velocity of particle 1. And then, in order for this to be equal to 0, either the final velocity of particle 1 has to be 0, or this has to be 0. Once again, the final velocity of particle 1 is 0. It just means that the final velocities are the same as the initial velocities. We haven't had the collision. So what we want is the solution where this thing is equal to 0. So I take that, set it to 0, and then it's just a matter of doing some algebra to find the final velocity of particle 1. So there it is. Now to find the final velocity of particle 2, I had an equation for the final velocity of object 2, right, that I plugged into the kinetic equation to get rid of that. Now we just have to take my solution for the final velocity of particle 1 and plug it into that and do some simplification. And here then is the final velocity of particle 2. So now I have the final velocities of both particles, but I have them in the transformed reference frame. So the final step then is to convert back to the original frame. And I do that by saying, well, remember I said that the velocities in the transformed frame are just the velocities in the original frame minus the velocity of particle 1 initial, the velocity of the frame we transformed into. So I have my equation for the final velocity of particle 1 in the transformed frame. I just changed my w's to v's using this definition that I created right from the beginning. So w1 final is the same as v1 final minus v1 initial, and w2 initial is the same as v2 initial minus v1 initial. All right, and then I just have to solve this for v1 final. I just add v1 initial to both sides, and then I do some simplification, just some basic algebra stuff, and then I find that my final velocity is this. So here's the final velocity for particle 2. Then I can do similar things for particle 1, right? I take its find the final velocity I found for it in the transformed frame and then transform back. However, another thing I could do is I could say, well, look, there's nothing special about labeling particle 1, and particle 2, particle 2. I could have changed their labels, and there's some symmetry here. So you realize, oh, if I have the solution to one of them, I should be able to just swap the 2's and 1's everywhere, and it should still be true, right? And then I have a solution for the final velocity of particle 2 in the original frame. So that was how we did the approach where we transform into a reference frame where one of the initial velocities is 0, solve it, and then transform back. Now let's see how we can solve this by going into the center of mass frame. To go into the center of mass frame, what I'm going to do is I'm going to convert the velocities into the center of mass frame, just like we did before, only now we're going into the center of mass frame rather than the frame where one of the initial velocities is 0. What's special about the center of mass frame? Remember, in a previous video, we talked about how the initial and final momentum are both 0 in the center of mass frame. So you can solve for the initial and final velocities of particle 2 in terms of the initial and final velocities of particle 1, then plug that into the energy equation to solve for the final velocity of particle 1. And it turns out there's going to be some ambiguity about the sign. We'll have to think about that to figure out what the sign of the final velocity is. And then you can take your result for the final velocity of particle 1 and plug that in to get the final velocity of particle 2, or we'll use symmetry like we did in the previous problem. And then once we have our final velocities for the two objects in the center of mass frame, we just transform back to get them in our original reference frame. Okay, so let's start by converting the velocities into the center of mass frame. And I'm going to use c to represent the velocity of particles in the center of mass frame. So the initial velocity of particle 1 in the center of mass frame is the initial velocity of particle 1 in the original frame minus the velocity of the frame we're transforming into, the velocity of the center mass frame. The initial velocity of particle 2 in the center mass frame is its velocity minus velocity of center mass, and so forth. So here is my transformation. Here's how the velocities change when I transform into a reference frame that is moving at the velocity of the center of mass. So now with those definitions, I'm going to note that the initial and final momentum are both 0 in the center of mass frame. This allows me to solve the momentum equation to find the initial and final velocity of particle 2 in terms of the initial and final velocity of particle 1. All right, so in the center of mass frame, the initial and final momentum are equal to 0. So my conservation of momentum equation looks like initial momentum of particle 1 plus initial momentum of particle 2 is equal to the initial final momentum of particle 1 plus the final momentum of particle 2, but both of those equal 0. So now I can break the momentum equation up into two equations. One equation is simply this side of the equation is equal to 0, and I can solve that for C2 initial, all right? So this is equal to negative that, and if I divide by mass 2, C2 initial is just negative mass 1 over mass 2, so I'm C1 initial. And then I can take this side of the equation, that's equal to 0, so that gives me this equation. I can solve that for C2 final. So now I have an equation for C2 initial in terms of C1 initial, and an equation for C2 final in terms of C1 final. So I can plug those now into my kinetic energy equation and totally get rid of the velocities of particle 2 and just get something I can solve then for the final velocity of particle 1. So that's the next step. Plug into the energy equation and solve for the final velocity of particle 1. So my kinetic energy equation is just initial kinetic energy of particle 1 plus initial kinetic energy of particle 2 equals a final kinetic energy of particle 1 plus final kinetic energy of particle 2. But I have these relationships for the initial and final velocities of particle 2 in terms of the initial and final velocities of particle 1, right, that I found earlier. So I just plug those in. As you recall, they had minus signs, but when you square them, the minus signs go away. All right, and then what I'm going to do is I'm going to actually combine these terms, right? So I have a C1 initial squared here and a C1 initial squared here. So I'm going to have just a bunch of rearrange things, so it's a bunch of stuff times C1 initial squared. Same thing over here, but for C final. And notice when I do the algebra, the thing sitting in front of C1 initial squared on this side of the equation is exactly the same as the thing sitting in front of C1 final squared on this side of the equation. So they cancel out, and I'm just left with C1 initial squared equals C1 final squared. Okay? So that means that the final velocity of particle 1 in the center of mass frame is either equal to its initial velocity or equal to negative its initial velocity. So the next step is to use reasoning to determine the sign. Well, if C1 final equals C1 initial, that's the case where the particles missed. We didn't actually have a collision. All right, that yes, the momentum and energy will be conserved if the velocities don't change. That's not the solution we wanted. We want the solution where they have changed, but energy and momentum are still conserved. And so that's our solution right there. So the final velocity of particle 1 is equal to its initial velocity in the center of mass frame. All right, then you can plug things in to get velocity of particle 2, or we can just use symmetry. Right? Once again, there's nothing special about calling one particle particle 1, the other one particle 2. So we can just kind of intuitively say, oh, the final velocity of particle 2 must be negative its initial velocity. All right? And so there you go. So in the center of mass frame, the final velocity of each particle is just negative the initial velocity. The particles fly in and then they fly out in the exact opposite direction with the same speed. So, for example, here we have our particles. They collide elastically. If we go into the center of mass frame, what does this look like? I just have these two particles come together, they bounce, and they come right back out. Here's another example where I have a smaller, faster moving ball. Here we go. Here comes a collision. Boing. All right, so we get this collision in the center of mass frame. What does that look like? the two particles just collide head on and turn around and go back in the opposite direction they came from with the same speed. All right? So there we go. We've got our solution. Now we just need to transform back. So remember, V1 final is just C1 final plus the velocity, the center of mass. So to transform into the center of mass frame, we subtracted the velocity of the center of mass. To transform back, we add the velocity of the center of mass, right? So C1 final was V1 final minus V center of mass. That means V1 final is C1 final plus the velocity of the center of mass. So remember, C1 final is just negative C1 initial, so I'll plug that in here, and then I say V1 final is just negative C1 initial plus V center of mass, and then I need to transform this back into the initial frame, once again by adding the center of mass. So this is going to be negative, by C1, V1, to get to V from C we add, to get from C to V we subtract the center of mass. So there we go, and then we just simplify that and we find that V1 final is just twice the center of mass minus V1 initial. Now we need to know what the velocity of the center of mass is. We kind of just smoothed over that, pretended like we knew it. Remember, we derived this in a previous video. We just said, oh, the center of mass for the two objects is m1r1 plus m2r2 divided by the sum of the masses. And then we said, oh, to find the velocity of the center of mass, we just take the derivative of this and our r's become v's. And so that is the velocity of the center of mass. There's our solution. We just simplify it, and this is what we get. This is the same solution we got before. Okay? So now we've gotten this solution two different ways. And then once again, by symmetry or by doing the transformation in the algebra, we get our equation for the final velocity of particle 2. So this is the same thing we got before. We've done it two different ways. Now we're going to do it a third way, which is we're not going to transform into some other reference frame. So this is, in a sense, a little more intuitive, except that there's a trick, okay? So we're not going to change reference frames. We're just going to barrel right through this, all right? In this method, what we do is we write down the conservation of momentum and kinetic energy equations. We're going to cancel out the 1/2 factors in the kinetic energy equation to make the equation look simpler. And then we're going to rewrite both the conservation of momentum and the conservation of kinetic energy equations. We're going to move all of the object 1 terms to one side and all of the object 2 terms to the other side, and then factor out the mass, okay? And then, once we've done that, we're going to use a little trick. We're going to note that a squared minus b squared is a minus b times a plus b. We'll rewrite the kinetic energy equation with that, and then we'll divide the momentum and kinetic energy equations, and magic will happen, and then we can solve for one of the unknowns, plug it into the momentum equation, and eliminate it, and get our solution. So these first 3 steps I'm going to kind of do at once. We're going to write down our conservation of momentum and our kinetic energy equations. For the kinetic energy equation, we'll get rid of the factors 1/2. And then we're going to rewrite both equations with all of the object 1 stuff on one side, all of the object 2 on the other, and factor out mass. So here we go. For the momentum equation, we have initial momentum of particle 1 plus initial momentum of particle 2 equals final momentum of particle 1 plus final momentum of object 2. So now we're going to move all of the mass 1 stuff to one side and all of the mass 2 stuff to the other. So I'm going to subtract this to get it over here, and I'm going to subtract this to get it over here. All right, and what we end up with then, if we factor out the masses, we just have mass V1 initial minus V1 final equals mass 2 V2 initial minus V2 final. All right, so there's my momentum equation. And we've done the first 3 steps on the momentum equation. Now let's do them on the energy equation. So we have initial kinetic energy of 1 plus initial kinetic energy of 2 is equal to the final kinetic energy of 1 plus the final kinetic energy of particle 2. So we said we're going to cancel out the 1/2 to make it simpler, and then we're going to move all of the mass 1 stuff to one side and all the mass 2 stuff to the other. So I'm going to subtract m1 V1 final squared from both sides, and I'm going to subtract m2 V2 initial squared from both sides, and then factor out the mass, and that gives me this. So there we are. Here are our two equations. Here's the equation that we got from manipulating the conservation of momentum equation, and here's the one we got by manipulating the conservation of kinetic energy equation. So this is conservation of momentum and kinetic energy. We've just rearranged terms, getting all the mass 1 stuff on one side and mass 2 stuff on the other. Okay, so now we're going to note that a squared minus b squared equals a minus b and a plus b times a plus b, and we're going to use this to rewrite the kinetic energy equation. All right, so we have v1 initial squared minus v1 final squared. I can write that as v1 initial minus v1 final times v1 initial plus v1 final, and we'll do the same thing over here for particle 2. So there's my kinetic energy equation. So we rewrote it. Now we're going to divide the two equations, the kinetic energy equation and the momentum equation, and magic will happen. So after using this trick, this is what our kinetic energy equation looks like. This is what our momentum equation looks like. And notice I have mass 1 on this side. I have negative mass 2 on this side. I have this factor here. I have this factor here. So if I take the energy equation and divide by the momentum equation, the masses will cancel out. This term will cancel with that. This one will cancel with that. And I'm just left with this equals that. Okay. So now I've kind of taken information from both equations. I still have two unknowns, so I still need two equations. So we're going to actually end up taking this along with the momentum equation and solving those two equations, right? We don't need the kinetic energy equation anymore because we've kind of taken information from it and put it into there. So with this equation and the momentum equation, we have two equations, two unknowns. But just as an aside, what we're about to do in the next step is we're going to take this equation that we found by doing our tricks and the momentum equation, and we're going to then combine them, do two equations, two unknowns to find our solution. So if you can't remember the solution, one thing you can do is you can say, if I just remember the conservation momentum equation, and for an equilibrium, an elastic collision, v1 initial plus v1 final equals v2 initial plus v2 final, then you have everything you need to solve it. You can kind of skip some of these steps that we did. Anyway, now the final step is solve for the one unknown, plug it into the momentum equation to eliminate it. So here we go. So I've got this equation. I'm going to solve the equation we found by doing our tricks for v1 final. So I'll just take v1 initial to the other side. Now I have this equation for v1 final. I can plug it into my momentum equation. All right, so we'll plug it in here. And then it's just a matter of algebra. I simplify some things, and then I only have initial velocities and v2 final. I can solve for v2 final. Okay, so it's just a matter of doing some algebraic manipulation, and I get my solution, v2 final. All right, and then either by symmetry, I can get v1 final, or I can take my equation I had for v1 final in terms of v2 final and simplify that. But there are my solutions, and these are exactly the same solutions we found two other ways previously. The final way of solving this problem is just remembering those are what the solutions are. But again, just memorizing the solutions is not as useful as knowing how to get them, because maybe you're working a problem where you don't have both initial velocities or you don't have both masses, right? Maybe you're solving for something different. And so it's good to know how these approaches work. So here's a problem we're going to solve now. A baseball with a mass of 145 grams traveling at a velocity of 37.2 meters per second strikes a baseball bat with a mass of 944 grams moving at a velocity of 18.3 meters per second in the opposite direction. How fast will the ball be moving after it hits the bat? Assume that the collision is elastic. Okay, how are we going to solve this? I'm going to solve it by remembering the solution. All right, there's our solution. So we just have to plug it in. Wait, are we really going to wimp out like this? Well, yeah, we've already gone through all of the algebra of solving the two-body elastic collision problem 3 different ways, and so I'm ready to be done with that. Let's just remember, the ball's initial velocity, we've got the bat's initial velocity, we know the ball's mass, we know the bat's mass, we have our solution that we remember. So let's just write this in terms of the ball and the bat. All right, so the final velocity of the ball, we just replace 1 with ball, do with BAT, and there's our solution. Just plug stuff in, plug our numbers in, and we find, the final velocity of the ball is negative 59.0 meters per second. All right, so we're assuming that the initial velocity of the ball is in the plus direction, so the ball comes out in the negative direction. And that's all, folks. Hope this was useful for you.